This is a set of Genaille Rods, which were invented in 1891. You can use them to multiply a big number by a single digit. Each rod has one digit on the top as a label, and then lots of little lines and numbers down here. These lines better be right or else it won't work. Here's a set that does division. They look even crazier. Each set has a special stick called the index rod, and the division set has an extra rod for the remainder. When you want to multiply or divide, you line these things up just right and they tell you the answer. Genaille rods are also called Genaille-Lucas Rods. Lucas was a famous French mathematician. I guess it should be pronounced Lucas. Among other things, Lucas showed by hand that this number is a prime number. That was the record largest prime number ever discovered before electronic computers found much larger ones. Anyway, Lucas gave a talk where he posed some kind of computational question, and Genaille, who was a train engineer and an amateur math fan, heard about this. He ended up solving Lucas's problem, and in the process he got the idea for this new kind of calculating device. People usually say that this is a variation on Napier's bones, which is a simpler looking device invented about 300 years earlier by Napier. I did a video about those too. Genaille's rods are physically similar to Napier bones, but they work on different principles. Napier's bones are based on something called lattice multiplication, but Genaille's rods, to me, are much more closely related to the standard process I learned in school for multiplication and long division. The bonus with Genaille's rods is that you don't have to do any computations in your head. When you use Napier's bones, you have to do some simple additions to get the answers, but with Genaille rods, it just tells you the answer immediately. The thing these rod systems all have in common is how you set up your computation. The set is always used to multiply or divide a big number by a single digit. So here's how you'd multiply, say, 7 times 4289. You line up the rods to spell out the big number, 4, 2, 8, and 9. Then you put the index rod on the left, line them up good. You look down to the row marked 7. Now you read the answer from right to left in this row. The rightmost digit in the answer is the top number in this row, which is 3. Now you move across the rods to the left, and you follow inside the triangles like little funnels. So the next digit is 2, then 0, then 0, then 3. So the answer is 30023. It's pretty crazy, right? Let's try one with the division rods. The division rods are actually a bit nicer to use because you read the answer from left to right. So let's try this one. You line up the digits of the big number in the same way with the index rod on the left, and this time with the remainder rod on the right. This time you just start on the top left and follow the lines across each time. I got 0, 4, 9, 7, 3, and a remainder of 5. So that means the answer is 4973 and 5/6. That's pretty wild, isn't it? There's obviously no secret mechanism or trickery at work, so the device is totally transparent, but at the same time, it's entirely inscrutable. There doesn't seem to be any rhyme or reason to the lines and all these little numbers that are written on each stick. I'll try and give you an idea of why it works. Here's a quick version. The little numbers on the rods give the different answers, digit by digit. And the little rows and lines from one rod to the next represent the carries. Let's look at this example, 479 times 6. If I work this out by hand, it looks like this. What we're going to see on the rods is the individual digits in the answer will appear as the little numbers on the rods themselves. And the carries are represented by which little row we jump to. That's why moving down by a row always increases the little number by 1 on the rods, because it represents a carrying of 1. So when I look at 9 times 6 here, the answer is 54, which is why I see a 4 in this position. And then the lines jump down by 5 positions to represent the carry of 5. The next column is 7 times 6, which is 42. That would be a 2 on the rod and the lines jumping down by 4. But in this example, I already arrived 5 positions down, so I'm going to get a 7 on the rod, but still the lines are going to jump down by 4 for the carrying the 4. That's exactly what I want to see in the answer. The answer is 7 with a carry of 4. Keeps going like this all the way to the left until you hit the index rod. and the final carry position becomes the leftmost digit in the answer. Pretty great. Here's something I noticed about the Genaille rods. Probably some other people have realized this, but actually I've never seen anybody mention this anywhere. Just like on Napier bones, they're meant to be used for one big number divided by a single digit. That's the way it needs to be for Napier's bones because of how lattice multiplication works. But the Genaille rods actually don't have that restriction. On my set, the index rod goes down to 9, but there's no real reason why it has to stop there. Like here's a set you could use for dividing by 38. There are 38 different possible remainders, and so the sticks need to have 38 little rows with lines for each one. It's probably not too practical, but if you want to divide by 38 all day long without a calculator, this may be just what you need. Actually, I generated this picture with some code on my website. You can click on over there if you like. I guarantee you it's the only place on the internet where you can auto-generate Genaille rods with rows past 9. Anyway, I think these things are really great. What's interesting to me is they were invented in the 1890s, but they didn't use any real modern mathematics of the time. They could have been invented by anyone who knew the Arabic number system, which had been around for about 1,000 years. So this is a pretty unique bit of computing history. Most computing devices are invented in response to some kind of new development, like new mathematics led to the slide rule, or new types of precision manufacturing allowed the big heavy machines in the early 20th century, or new types of electronics led to calculators and computers in the late 20th century. But Genaille invented these rods without using any new anything. He was just working on the railroad and thought of something that nobody else had ever thought of, even though the basic concepts had been available for about 1,000 years. That's what historians call gangsta.